Good morning. I'm here to talk about some of our project work. It's a kind of an informal collaboration with a CFD provider and myself. It's been going about 3 years now, so it's kind of a good time to summarize what we've done, and we're very lucky to be able to present it here. So today I'll share with you the project team, some of the motivations of why we just started doing this, a bit of the background of how we did this, and more importantly, we'll be talking about some benchmarking studies that we did, and then more importantly, also the transient simulations that we recently completed just prior to publishing this paper. Then we'll kind of finish up with talking about the challenges that we faced and kind of the conclusion. So really quickly on the project team, I'm from my heart, as Dr. Lee has mentioned. We're engineering consultancy. We do structures, MEP and facade. Basically, it's all in-house. We have about 3,000 global staff. We're currently headquartered in Singapore, where I'm based. The CFD providers, they're Cradle, and they're headquartered in Japan, but we collaborated with the office in Dayton, Ohio. And my co-authors are Sunil and Yuya. I wish they could be here, but I'm going to have to present on their behalf. Okay. So, kind of like the context for all this, right? Everything that we do needs to have a context. So it wasn't really just kind of using CFD for CFD's sake, but really the context of the research of the project was the design environment that we operate in right now. So as many of you know, we are under tremendous pressure from accelerating design cycles, whether we're MEP engineers, structural or architectural, and that's kind of been pushed, from economic pressures, but also because of the proliferation of digital design tools. So that allows us to do more things more quickly. Layer on top of that, we have parametric design. So not only can we do things more quickly, we can do more options in the same amount of time. And all these things, one would think would be very expensive to execute, but actually that's not true, because a lot of the tools are actually pretty low cost compared to what they might be. And a lot of software is now open source. So you actually have a lot of tools that you can deploy on your projects that allow you to do things pretty quickly. So I'm going to come at it from a structural perspective as to what this means from us as structural consultants. So I'll talk briefly about three things as to where the technological frontier is for me, at least personally, and what that means as we go forward. The first one we'll briefly talk about is we're doing the peer review, a very in-depth peer review of the stadium roof in Singapore, and that requires it's got a lot of multi-planar connection nodes, as you can see here. And what we had to do here was analyze about 300 of these complicated connections, multi-braces coming into a single node. And because with the peer reviewer, we clearly don't have a budget as large as maybe the base engineer. So we needed to automate a lot of our work. And you see on the screen basically all these 6 tools that we've kind of linked together to generate FBA models like that. And so that clears out a lot of man hours in terms of labor. And really that allows us engineers to focus on the value-added things, actually to verify that the stresses or the models are generated correctly, as opposed to a lot of the manual work you can imagine to generate that, from geometry to loading to meshing. Thanks. Okay. So this is just illustrating the link. If you're familiar with Rhino, it's on the left, and Grasshoppers on the right. But just illustrating how, as structural engineers, we can use traditional architectural tools to work with their design surface and to evaluate structural options pretty quickly. For those who were here last year, this is the same thing. So how do we go from being able to do very quick structural analysis and verification? And the question this year is what's next after you are able to do something like this? So there's a example tower where we're looking at, we can plot out the wind pressures, the base moments and shears on the design surface itself. We can naturally layer on structural information such as the bracing or perimeter beam scheme. And once we're done with that, we can immediately drive that all to FEA. So we have a very tight link between the architectural geometry and the structural solutions. So we can explore it from a massing standpoint, on a gross basis, and we can also explore it in depth. So now this is all real time, so you can imagine that with the accelerating design cycles, we're actually able to execute analysis a lot faster than we're used to do. So second video is about optimization. So now that you're able to generate all these options in a really quick manner, like the real question from us at least structurally is, how do we optimize the solution? When we say optimize from the structural perspective, usually means controlling drift. So here we're looking at controlling drift at 3 locations along a tower's height, a hypothetical tower, in both the x and y directions. So we have 6 constraints that we want to impose on the solution, and we're also looking at constraints such as volume. So columns cannot be any larger than x, or cannot be smaller than y. So this is a custom program that kind of like sets that up. And this is all VB.NET, and it's laid on top of open source optimization technologies. So we're able to very quickly nowadays generate the model. Okay, look at it from a growth standpoint. Generate the model and optimize it in pretty fast times now. So with the structural realm addressed, the question in my mind was, okay, what's next, right? So we can design for these loads, these wind loads, typically for high-rise building. But the question is like, how can we actually mitigate or lower those loads as much as possible? So this is the context for the CFD project that we undertook. Okay, so in the age of freeform architecture, the geometries get more complicated. We can lay on pretty much custom workflows with very low cost tools, open source tools, and design cycles. The question in my mind was like, what should the form be? So from the structural perspective, when we start our project, these are kind of typical questions. And I'm sure many of you in the room have worked on many high-rise buildings, and you send your building off the wind tunnel, and you hope most of the time that the loads you've assumed are going to be conservative enough. If not, you have to go through that kind of painful process with the design team as to say like, you didn't guess quite right. So the question becomes is like, are the code loads conservative enough? Will the proposed tower, if it's sharp angular corners, will that be having significant cost response? Or if you're in a building in an urban environment, are you getting subject to buffeting from surrounding towers? And then if the answer to these two is yes, usually we get suggestions from the wind tunnel that maybe you can do some color modifications, venting area or tuning on structural properties. So that's all good, but the problem with that is that usually it takes some time. There's a lead time to anything you start, and so the question becomes like, can we in-house that a little bit so that when we actually consult with the wind tunnel, we're actually proposing solutions that we think are going to be quite beneficial. So we'll go through two things we did. The first thing we did was look at some steady state simulations, which means it's a mean response. So that's good for the drag load, but of course that's not so great for the crosswind load. So the mean response, the final state is independent of time. That allows us to take large time steps. Actually, allowed us to do full 3D models. So once we were happy with that, we kind of calibrated that. We looked at some transient simulations where we could capture transient phenomena such as vortex shedding or buffeting. So the first thing I'll take you through is kind of like the steady state simulations that we did. Those 3D models with the surrounding environment. What we had to do was extract out the mean wind tunnel response. So that would be that middle line that you might be familiar with. And we wanted to compare 3 things. We wanted to compare the wind tunnel loads, the prediction of the wind tunnel loads from the wind tunnel, CFD, and also the building code loads. So how do we, when you first start a project, you don't have the wind tunnel, you don't have CFD. You would just look at, the building code. But the building code obviously doesn't account for surrounding buildings or sharp corners or things like that. So what we did was kind of extract out the surrounding buildings, and this is the Petronas, and our building is this green one right here. So we're kind of close to the Petronas, and the question, this was all tested and built already, so we have good data set. Do we have shielding or do we have buffeting? How can we see that from a computational perspective?
Just a bit of benchmarks. We had a tetra mesh about 36. This was done at the Cradle site, so they had a huge computer cluster, and they just basically, I set up the geometry, and they went away for a while. They came back a few months later and said, "This is what we did." It wasn't a full-time thing, so it's like as they had time, they kind of worked on it, and we talked about what the results were. But just looking at some raw statistics, they did all 36 directions. Congratulations to them. They did about 8 hours per direction. So these are not unreasonable run times. And naturally, if you were to do it in-house, you would not test all 36 directions. You would kind of test the critical directions, which you can observe from the surrounding geometry. The plan view of what the test was, up in the bottom upper left, the Patronus, and these are our reference axes. That's a close-up mesh view of the mesh. They kind of rotated around the global domain. So the first one is the MX load. So we see 3 lines on the screen. The wind tunnel is the orange line. The CFD prediction is the purple, and then the base building code is the cyan, I guess. So it's all normalized, but you can see that the trend is pretty good. So between the 3 things. So as you rotate the building around the 360 degrees, the MX load increases and then decreases. Okay, can you go back, please? Okay. So as you rotate the building around, the building loads, the building base moments is what we're focusing on, kind of trends similarly. And actually, when we got this, we were pretty excited by it, because when we first started this about three years ago, just casually asking your colleagues, like, if you had to do a CFD on some buildings, what do you think the response would be? And we had like responses of, it will be like orders of magnitude off. It wouldn't even be close. The runtimes would be astronomical. And after going through this exercise, we actually found that that's not really true. We are in the realms of predicting the mean response pretty decently. The second direction is the MY direction. So the same thing. The orange and the orange is the wind tunnel. The purple is the CFD, and the cyan is the building code. So obviously the building code can't really account for shielding effects. So that's the load you would typically design for. But if you were able to identify, in this case, a positive effect of surrounding buildings, that could be beneficial for your design. And here's a graphical of the shielding effects. So we did actually two base kind of like benchmarking. For instance, for the sake of time, we'll just show one. The second one's in the book if you're interested. The second, so after we done with like the mean response, we started like look at the transient simulations. And so in this situation, you need like a much smaller time step and a much more refined mesh. But what we were looking for is can we identify some crosswind loading, some buffeting, and can we look at what kind of mitigation strategies could we employ, could we explore computationally before taking that to the wind tunnel. At this time, we were pretty lucky in the office. We did a peer review for high-rise building, and the one on the right is the proposed tower. So naturally, for those who are structurally inclined in the room, you'd be asking, well, that looks great from a wind perspective. So what we wanted to do for this project is compare what if we had a solid case. So just some basic statistics, a much smaller model, but now it's a transient simulation, so the runtimes were longer for that smaller model. And this was done actually in the Singapore office, so this was without the computer cluster. We just ran it on a regular, it's like 6-core desktop. And we had runtimes in the order of like a day. So these are, again, not unreasonable runtimes, especially if you take the weekend off to come back on Monday and see what happened. So here's the model setup. On the top, you have the solid case with the sharp corner, so that's all structurally very bad. And then the bottom, we have the mid-height atria. So what we wanted to do was compare the response in here versus here, so which is the beneficial response. So, and before we ran any computations, we wanted to see if we could, how the computations would be from prediction of the shedding frequency. So that's kind of interesting. We want to tune the structure away from the shedding frequencies to make sure we don't have that resonant response in there. Okay, so let's say on the upper one, we predicted about 10-second shedding frequency. Okay, so here are two animations. The upper one is obviously the solid case where we can see that the crosswind response. This is all in 2D. And if you could click on the bottom animation for me, please. Yeah. Hopefully that runs. So we see that benefit. So that's all very kind of cool from a graphical standpoint. But what we did was extract out the loads, the predicted loads in the crosswind direction. So let's see if this goes forward. Okay, so here we have, so it's kind of a busy plot, but we're looking at the along-wind and the crosswind response, both for the solid case and the vented case. So the lines without the squiggles are the solid case. So this is the along-wind response for the solid model, the crosswind response for the solid model. Oh, sorry, this one. And when we look at the peak to peak, we're actually seeing at prediction of the frequency, the shedding frequency about 10 seconds. So that's kind of good. Like basic hand counts kind of verify like what's coming out of the computer. The other thing that was interesting was looking at the reduction in the crosswind response from the solid case from the vented case. So the purple line versus this yellow line. So actually we're able to reduce, bring down that crosswind response pretty significantly by this mid-high area. So it's nice that it was built into the building already, but we'll kind of be able to do something after the fact to see what it would have been. So this is good that we're able to pull out the frequencies, but the other thing we noticed in here was there's a long period in here for the vented case, and of course there's other shorter periods in there. So what we wanted to identify was the shedding frequencies for the vented case as to okay, what do we need to make sure that the structure is tuned away from. So the long period here, that's about 15 seconds, and then there's other frequencies in there, and that goes down with the FFT. So that was kind of nice, but obviously it's a 2D model, so that ignores the 3D effects, right? When you have a high-rise building, the vortices aren't correlated all the way up and down the building. So that's one issue. The second one was we were able to actually reasonably predict with the shedding frequency, so that's kind of good to know beforehand what do we need to do structurally to be able to move the building behavior away from those resonant frequencies. And we also able to look at vortex shedding mitigation strategies. So in this situation, we looked at venting, but of course, quantum modifications were the same effect. So very quickly, I guess a couple of more minutes, I'll run through a bit of the project challenges. We did this in 2 different offices. They're based in Dayton, Ohio. I'm currently based in Singapore, so it's a bit of time difference, but that's one thing. But from the CFD perspective, these are pretty large models, even by their perspective. For them as a software provider. Now they're not a commercial site, so they think they told me they have 128 cores, which sounds like a lot to many of us in the room, but actually that's not in their industrial world. So we all had to kind of grapple with the large model sizes and moving that data back and forth between Dayton and Singapore. Some hardware challenges, data management, more hard drives, more RAM, always good. One thing I had a little bit of issue was incorporation of surrounding buildings or forms. So we did a kind of a hack, just getting out of Google Earth. That's not the best, but obviously wanting to do this, you need to actually build in the surrounding building information to get that buffeting or shielding effect identified. So the future work, I'll quickly wrap it up. We'll like to look at mesh dependency studies. We definitely, I think when we first started this, they really meshed it out quite high. I think more recently, last few months, they were able to reduce the model size and actually not change the results too much. Time set dependency, 3-dimensional effects. How do we reconcile 2D and 3D simulations? And since this was the first time we were all doing it, we'll look at geometry importing, analysis, post-processing. Those all kind of had to be done a bit manually this round. So I don't think this replaces physical testing, but I think that it's an opportunity to complement, the structural design process and the wind tunnel testing. So we think that CFD has the potential to complement the usual design process that we used to. We definitely think that it can aid the initial form of the high-rise buildings. How do we deal with vortex shedding, crosswind buffeting early on? Identify it, communicate it. The graphics are great for communication. And if there is a problem, then now we can use it as a platform to study some mitigation strategies. So that's my presentation. I definitely want to thank the leadership at Meinhardt, Cradle, Halverson. So this study was kind of started back in 2010, and we use a whole slew of platforms, some proprietary, some open source, to kind of push to get the project done. All right, thank you.